Okay, think about this for a second. We're constantly surrounded by stuff we can't see, right? Like gravity, which is literally holding you in your chair, or the wind you can feel but can't grab. Well, today we're going to pull back the curtain on how scientists actually see these invisible forces. We're diving into the mathematical language they use to map out this unseen world. It's going to be cool, I promise. So let's just jump right in with a question. How in the world do you draw a map of something that's invisible? I mean, seriously, how do you map the pull of gravity or a magnetic field? It sounds kind of impossible, like a riddle, but it's a puzzle that scientists deal with every single day. You know, the answer is actually hiding in plain sight, and it starts with something I bet you've already looked at today, maybe even on your phone. Yep, a simple weather map. All right, so let's take a closer look at this everyday tool, because once we peel back the layers, you're going to see that it's so much more than just a way to check if you need an umbrella. It's actually a super powerful mathematical idea hiding in plain sight, a whole new way of looking at the world. So this is where we need to shift our perspective a little bit. A weather map isn't just a picture. It's better to think of it as a field of data. Imagine every single point on that map, and I mean every point, has a little sticky note on it with a number. It's a massive collection of information. Okay, let's dig into that idea with our first big concept. We'll start with something really simple that you'd find on any weather map: temperature. I mean, really think about it. If you could just point to any spot on that map, your house, the coffee shop down the street, the top of a skyscraper, what information would you find there? Just one thing, right? A single number: the temperature. That's it. Now, in the world of physics and math, there is a special name for any quantity that's just a single number, just a magnitude. It's called a scalar. Temperature is a classic example. But so are tons of other things, like your height, the weight of your dog, or the price of a gallon of gas. It's just a number. So here's the cool part. When you take a whole area, a whole region, and you assign one of those scalar values to every single point in it, bam! You've just created what scientists call a scalar field. And that's all it is. That's the fancy scientific name for our temperature map. And really, that's all there is to it. It sounds complex, but the idea is super simple. You pick a spot, you give it a number. Then you pick the next spot and give it a number. You just do that over and over and over again for the entire area. Okay, so a single number, a scalar, works great for temperature. But what about something a little trickier, like the wind? If I just tell you the wind's speed, is that enough? Does that really tell you everything you need to know? No way, right? Of course not. To really understand the wind, you need two things. You need to know how fast it's blowing, for sure. That's its speed. But you also absolutely need to know which direction it's blowing. Is it a north wind? Is it coming from the west? That direction is just as important. And that little problem brings us to our second huge concept for today, the vector. A vector is any value that has both of those things we just talked about: a magnitude, which is just a number, and a direction. That's why we almost always draw them as arrows. The length of the arrow tells you how strong it is, and, well, the direction it points tells you the direction. Simple as that. So, following that same logic, what do you think our wind map is? It's a perfect example of a vector field. Instead of just a single number at every point, now we're putting a little arrow, a vector, at every single location. And that one arrow tells us everything: the wind's speed and its exact direction, right there at that one spot. Okay, let's just boil this all down to the key takeaway. You got a scalar field, like our temperature map. It gives you one piece of info at every point, a number. Then you've got a vector field, like the wind map. It gives you two pieces of info, a number and a direction. That is a fundamental difference, and it's a super important one. Now, this whole idea of creating fields to map invisible stuff, this isn't just for weather forecasters, not even close. This is one of the most fundamental, most important tools we have for understanding how the entire universe works. It's huge. Take gravity, for instance. We describe gravity as a vector field. Just picture it, an invisible arrow at every single point in space around the Earth. Every single one of those arrows is pointing directly toward the center of the planet, and the length of the arrow shows you how strong that pull is. The closer you are, the longer the arrow. Or what about the Earth's magnetic field? That's another perfect, beautiful example of a vector field. It's this giant map of invisible arrows that flow all the way from the magnetic South Pole to the North. And this is the field that makes your compass work. It's also what creates those absolutely incredible northern and southern lights. And then, of course, there are electric fields. These map out the force that a little charged particle would feel if you placed it at any point in space. This vector field, this invisible web of forces, is pretty much the foundation for, well, everything. Electricity, all of our electronics, pretty much all of modern technology runs on this idea.
So, okay, we've gone all the way from a simple weather map to the forces that literally hold galaxies together, which brings us to the big so what question, right? Why should you care? Why does learning this new language of forces actually matter?
Well, it matters because these fields aren't just pretty pictures. They're a language, and it's a language that lets us do three incredible things: describe, predict, and, this is the big one, harness the invisible forces that run our world. Whether we're talking about air pressure or the flow of ocean currents, this is how we actually build a model of reality that works. And that's really the heart of it all. These concepts, scalar and vector fields, they're not just for some abstract math test. You should think of them as the tools, like the grammar and vocabulary, that let us read the hidden story of the universe. They're how we translate the fundamental rules of everything into models that we can actually see, understand, and use. So, I want to leave you with one last thing to think about. Now that you know the basic language of fields, if you could create a map for any invisible force, any unseen pattern, or maybe even a feeling, what would you map? What hidden story out there would you want to bring to light?